So last time I spoke about Hochschild, Kosten, Rosenberg theorem. So let me give the algebraic version of this theorem. Let A be a commutative and smooth algebra over characteristic zero field. Then Hochschild homology of A are naturally isomorphic to the space of differential forms, Kähler forms of A over K. And the map, given this isomorphism, is given by the formula chi of, so it's the map from left to right, from Hochschild complex into differential forms, and is given by the formula chi of A0, A1. I use commas instead of tensor signs just for the sake of brevity. Goes to A0, dA1, wedge, dot, wedge, dAn. And Hochschild cohomology is isomorphic to a space of, let's put it this way, polyvector fields on A. That is the map given by well, you need to dualize this complex more or less. It's just a map from A linear maps from this to A. Yeah, homomorphisms. And the map is given by, it's a map from left to right. To C dot AA chi of phi, and you apply it to A1, AN, because you remember that this is equal just to the space of K linear homomorphisms from A and nth tensor power to A. So you just give it like this, and do it like this. It is equal to the pairing of phi with dA1 dot dAn. Now that's algebraic side of the story. The most delicate part of this is the smoothness condition, but the example, the basic example is just the algebra A equal to the symmetric algebra of some vector space, or just this algebra of polynomials with variables xn through xm. Let us now, it is our purpose now, because we are going to work with, it's our purpose to work with smooth manifolds. It is our purpose, it is our aim to go from algebraic case to, well, smooth algebraic algebras, algebra smooth in algebraic sense, to the algebra of smooth functions on smooth manifolds, so something you would probably call smooth in a naive sense of this word. So, what to do if A is equal to the C infinity algebra of some manifold M? Well, naively speaking, this algebra is smooth. But it is definitely not finitely generated. It's not even countably generated, of course. It's even, I think, uncountably generated. There are lots of topology there. So to avoid this topology, we want to modify our definitions of Hochschild homology. Namely, if you try to plug in C infinity of M into these morphisms, into the Hochschild-Rosenberg theorem, then, of course, the maps chi will survive. And it will induce the maps from the Hochschild homology of A into differential forms in the usual sense on M, right? Let's put it like this, C infinity of M, right? And it will induce the map from polyvector fields in the usual sense on M into Hochschild cohomology of this algebra. I think it was one of the exercises, if it was not, then please do it, to show that this map induces morphisms in cohomology in both cases, here and here, for all commutative algebras. So whenever you have a commutative algebra, you can define its scalar forms. You can define its, well, polyvector fields dualizing the scalar forms. And then you can define the maps just by using these formulas I gave you. And you can easily check that these maps actually commute with differentials, where you can consider the space of scalar forms and the space of polyvector fields as complexes with zero differentials, right? However, these maps are no more isomorphisms. And the reason for this is that the non-finitely generatedness of the algebra. It is too large to apply to it, to use the usual algebraic constructions when you work with it. So there are two ways to modify this statement to make the Hochschild-Rosenberg theorem work still, right? So there are two ways. So first, it is, I think it's more popular nowadays because it can be extended to non-smooth algebras, non-smooth algebras, non-commutative, non-smooth algebras like C-star algebras and so on. And that first construction is to introduce topology. Use topology. Namely, the algebra of functions on a smooth manifold in the topological space is always endowed with the canonical Hausdorff topology, compact open topology, right? When you say that two functions are close to each other, if they send some compact subsets of the domain into the same open set in the range of these functions, right? And this gives you the algebra of, well, if you consider, say, continuous functions instead of smooth functions, then you can use this topology to introduce a C-star algebra structure on the space of smooth functions, sorry, on the space of continuous functions. C of M is C-star algebra. Sorry, I'm using Russian. This is C-star algebra. And then you can modify the definitions of the Hochschild complex, for instance, of this complex, by using tensor products in the continuous category, the completed tensor products. In case of smooth functions of M, this will give you the following result. The algebra, the complex C star, so say Cn of A comma A, will be isomorphic to the space of smooth functions on the M+1 fold Cartesian product of M. Right? So you could have used this definition from the very beginning when you work with smooth manifolds and check Hochschild and check the Hochschild-Koston-Rosenberg theorem in this case, and it will work.
Which method defines this isomorphism?
I said that we use completed tensor product. We don't use the usual tensor product. We use completed tensor product. But the idea is very simple. When you have a pair of functions on M, you construct the single function of two coordinates just by taking the first function and calculating its value at the first coordinate and taking the second function and calculating its value at the second coordinate. And this gives you the function of two coordinates. In general, you just have a map from tensor product to the space of functions of two coordinates. But if you complete the tensor product in an appropriate way, then the result will be equal to just the space of all functions of two coordinates, of all smooth functions, or of all continuous functions, depending on how you define it. You could have actually avoided this by using this definition from the very beginning, right? But there is another construction, and this construction asks for, it works better with cohomology theory. And it asks for restricting the space of all maps. So cohomology, let me recall it, the nth space of Hochschild cohomology complex is equal to the space of all homomorphisms, k linear homomorphism from A to the tens of k n power to A, right? This space is pretty large if you just take all polylinear homomorphisms of this sort. However, if A is equal to C infinity of M, then you can restrict this space. And there are two popular ways of doing this. So let me give the definitions. These two constructions are pretty close, and in case M is compact, they even coincide. But let me just give the definition. So let phi be an element in this Hochschild complex for C infinity L functions on some manifold. Right? We will say that phi is local if phi of f1 fn is equal, it's a function again, right, on M. So this function is equal to 0 at a point x if or when there exists I from 1 to n, and there exists an open neighborhood U x of x in M, such that Fi, so x is here, of course, Fi of at this, when we restrict Fi at this open neighborhood, you get 0. So Fi vanishes identically at this open neighborhood. So in this case, we say that phi is local. It is easy to see that when you have some local cochain, Hochschild cochain, and its differential will also be local. It's a good exercise for you. Show that local cochains form a subcomplex in C star A, comma A. There is another definition, so that was part 1 of the definition. Part 2 goes like this. We will call phi differentiable cochain if phi is given by a Pauli differential operator. If phi is given by a Pauli differential operator. On M. So what is Pauli differential operator? So there are different ways to define it, but you know, it's like when you work with differential operators. There are different ways to define them, but the most standard one is by going to coordinates. So phi is a Pauli differential operator if in coordinates phi of f1 fn is given by the following formal sum. Some coefficients depending on I and on x. I is a Pauli vector, is a Pauli index, multi-index maybe. I1, In. And here we have di1 f1 dx1 I1, and so on. xn in. Of course, the sum should be finite, so probably we can probably put that module of I is less or equal to some large number n. But in general, it should look like this.
So by module we denote the sum of these.
Oh, sorry. Yeah, it's already incorrect, because actually it seems like I'm applying I1 just to the first coordinate to F1. It's incorrect. So actually, I mean, it's easier to explain than to write down the formula, because actually I need not one multi-index, but some kind of n multi-indices. In, In1, In, sorry. Oh, this n is incorrect, so probably better to put m here, right? Let it be m. M multi-indices. Imn. And here I have d mod I1 f1 dx I1. So dx I1 means that I apply I11 to I apply d over dx1 I1 times and so on. And here I have mod In, Im, right, Im, dim. And yeah, and the sum is taken by all the collection of i's. And again, it should be finite. So that's what they call the Pauli differential operators. Of course, the explicit coefficients a, I of x depend on the choice of coordinates, but whatever coordinate system you choose, the general outline of this construct, the general form of this expression will be the same. So this is a well.
A is just a scalar.
Yeah, just scalar function. Yeah, a general form of this expression will be the same in all coordinate systems. So it's a well-defined notion. Now, as I said, these two notions of local, and yeah, again, I think it's a good point to put the second exercise here, show that differential cochains again give you a subcomplex. It turns out that actually these two subcomplexes, these two notions, are more or less the same. So I denote these subcomplexes by log of a comma a and c star diff of a comma a. So they are more or less the same, and this is given by the following theorem, which is sometimes called Petrus theorem. Let x be a point in M, and let phi be a local cochain. So of course, in Petrus' paper, this was totally different. This was formulated in a totally different way. He didn't speak about Hochschild cochains at all. Then there exists an open neighborhood of x in M. And differentiable cochain phi u at this ux. So actually, this cochain will depend on the choice of u somehow, such that phi restricted to u will be equal to phi u. And actually, I'm not going to prove this theorem, of course. If you really want to see the proofs, you can find Petra's papers. They are available online, I think. But the general idea is pretty simple. The general idea is pretty simple. When you restrict something, so you choose coordinates. Choose coordinates. x1, xn around x. And so I'm trying to remember the details, which I don't remember actually. Then take functions f1. Okay, let's concentrate on the case when the degree of this phi is equal to 1. And take f1 given by some polynomial of the form, so f tilde be a I x I to the power of, so probably 1 n x1 to the power I1 xn to the power in. I also assume that x will correspond to the origin in these coordinates. Right? Then phi of f1 tilde will be given by linear combination of ai's. It's due to the locality, right?
It's just constant. It's not function.
Well, ai's times some coefficients, of course, times some coefficients, functions coefficients. And this allows you to restore the differential operator. And the most delicate part is actually to show that you can actually take only finite, only polynomials up to some finite degree. It turns out that it always exists some finite degree such that this f on an open neighborhood will be determined by finite degree of these polynomials. And that's more or less the idea, but of course the details are pretty lengthy and we don't have time to go into these details. We see that it follows the corollary is that if M is compact, then the differentiable complex, the complex of differentiable cochains, will be, it is always inside the space of local cochains, because every differentiable cochain is local. Well, it's almost evident, right? But in fact, it will be equal. Because for every cochain, you can define a finite number of open sets. And every open set, you have a differential operator of some finite degree. And then you just use the partition of unity to glue this finite degree differential operator to a common, to a unique differential operator on the whole space M. In general, there can be problem that the cochain, local cochain, is given, will be given by some infinite dimensional, not infinite dimensional, but by some differential operator of infinite degree. It can be, in theory, be given by this. Now, if we restrict our attention to differentiable cochains, that's what we are going to do from now on. In this case, we do have the Hochschild-Rosenberg theorem, which was proved in this form by a group of Belgian mathematicians in the end of 70s, beginning of 80s. And this achievement, this result allowed them eventually to give the first known construction of deformation quantization of genuine manifolds, although not of Poisson manifolds, but only of symplectic manifolds. So let me give this result. Theorem. Let Hochschild-Rosenberg map chi be given from a space of polyvector fields on M to the space of differentiable differential operators on M, a space of differentiable Hochschild cochains. A Hochschild-Rosenberg map. Then, for every cocycle alpha in this space of differentiable cochains, they exist a polyvector field P such that alpha is equal to Hochschild-Rosenberg map chi applied to to P plus the Hochschild differential D of some map of some cochain E, differentiable cochain. So it follows directly from this result that, of course, the Hochschild-Rosenberg map induces isomorphism in cohomology. Well, in cohomology, of course, on the left, cohomology, we just have the space of polyvector fields with zero differential. And on the right, you have the differentiable cohomology of M. And that's precisely the result we're going to use from now on. So whenever I speak about the Hochschild cohomology and Hochschild-Kosten-Rosenberg map, it will mean that I am speaking about the differentiable, smooth, differentiable or local Hochschild-Kosten-Rosenberg map. Sorry, yeah, Hochschild-Kosten-Rosenberg cohomology and differentiable or local Hochschild-Kosten-Rosenberg map.
Delta is differential.
Yeah, it's a differentiable in Hochschild-Kosten-Rosenberg. In Hochschild cohomology, Hochschild complex. Delta is differential Hochschild complex. Before I proceed, let me make one more observation about this remark. Consider the map. The map sigma, symmetrization map from Hochschild complex to itself. Well, A is commutative, of course. Therefore, this sigma will be will commute with the differentials. Otherwise, it will not. So this sigma of phi, when you apply it to f1, fn, it will be equal to 1 over n factorial, sum over all permutations s in Sn, minus 1 to the power n, phi of f s1, f sn. So just commute all the arguments in this map, and it is a good exercise for you again. Exercise show that sigma commutes with differential. In the sense that sigma of delta of something, of some cochain, let it be psi, will be equal to 0. Probably better to use something other. Commute is too much of a word. Yeah. Okay, that put quotation marks, I don't know. Because it's actually not commuting, but it actually kills the differential. So look here now. Look at this formula. Look at this formula. And apply sigma to both sides. Sigma of alpha on the left will be equal to sigma of chi. This sigma is, of course, linear. So we can just do it separately on chi of p and of delta of e. So the second term will vanish. Right? And the first term will be equal just to chi of p. So we see, conclusion. It's not theorem. Conclusion is that if alpha is a cocycle delta of alpha is equal to 0, in other words. Then the class of alpha in Hochschild cohomology is determined by its symmetrization. In other words, if sigma of alpha is equal to 0, then the class of alpha in cohomology is equal to 0. In cohomology. So, and that's actually the conclusion of this Hochschild-Rosenberg theorem, as it was proved by this Belgian group of guys. I think the most well-known people there are Marc de Wilde and I think Jean Leconte. And also the still active Simona Gut is also one of the members of this group. But the proof, well, I'm afraid the proof is pretty technical. The idea is simple, however, so let me just mention this idea of the proof. Idea of proof. Consider, so you have a polyvector field, right? And you have a polydifferential operator. So what is in common for all differential operators? It's common that they are described to a certain extent by their degrees. So since we work with polydifferential operator, we can introduce its polydegree, multidegree. So consider a multidegree, the multidegree, polydegree, I don't know, polydegree of the polydifferential operator. The polydifferential operators which correspond by Hochschild-Rosenberg theorem to polyvector fields, they are of polydegree 1, 1, 1, and so on, right? So we need to show that whenever a polydifferential operator has degree greater than 1, 1, 1, we can actually now we can use the lexicographic ordering to order the degrees. And then we can show that if the polydifferential operator has order greater than 1, 1, 1, and so on, then its class in cohomology will be equal to 0. So that's the first step. And to this end, we consider symbols of polydifferential operator. So a symbol of a differential operator, I hope you know what it is. It is a polynomial function which you obtain by substituting new variables xi1 through xi(n) instead of partial derivatives. But now you have n copies of the same partial derivative. So you need to consider a polynomial of n times m variables, which you can separate into m blocks, n variables in each. So you now consider, when you consider symbols, you can transfer the Hochschild differential from the algebra of polydifferential operators to the algebra of symbols. And then you can check this construction for symbols and use the reverse construction, which restores differential operator from symbols, to show that this is true.
How would you?
Sorry?
How would you?
Well, it's pretty complicated. It's then in several steps. It's not just a one-step process. You consider symbols. So you consider the filtration of symbols by the lexicographic order. And then you proceed by showing that when you have some property which you don't like, then you can always find the cochain which will fill this gap, like this. So you do this one step by step, and then you show that all off-poly differential operators of poly degrees greater than 1, 1, 1 in lexicographic order should vanish. And then when you are left with a poly differential operator of order 1, 1, 1 and maybe zeros, then you show that in order to survive, it should be anti-symmetric in all variables. And that's one more thing you need to prove. So you can actually look at this, but it's very technical, so I just skip it. I think maybe it can be of some use. I have never seen this construction, these methods. They were used by this Belgian group of mathematicians in the end of 1970s, beginning of 1980s, when they proved their theorem about the existence of deformation quantization in symplectic case. Meanwhile, while they were proving, they proved several interesting results, byproducts, which were quite interesting on their own sake. I have never seen these type of ideas, this kind of ideas being used by other people. Maybe they can be fruitful if you apply them to some modern type of constructions. I don't know. Maybe the time has come to pick up these ideas from the closet, blow away the dust from them and use them in new studies. Maybe, I don't know. So before I can proceed and go to the deformation quantization problem in its own right, I need to introduce some more structure on the space of differential operator. On differentiable Hochschild cohomology. Maybe it's better to use this notation. Less informal. So more structure. On Hochschild complex. There are two more operations which we will use, and one of them will be more important than the other, so I begin with something less important but easier to define. Let A be any algebra then for every two cochains phi of degree p and psi of degree q in Hochschild cochain complex of A, you can define their cup product by the following formula. When it will be cochain of degree p plus q, so it will depend on p plus q variables, p plus q arguments. And the result will be equal to just to the product of phi applied to the first p elements in the string, and times psi applied to remaining q elements in the string. It's a good exercise to show that this map verifies the Leibniz rule with respect to the differential, the graded Leibniz rule, of course. I think this is much easier than the second example of the structure that I'm going to talk about. So, and therefore I'm going to do this now. If I apply delta to the product, cup product of phi and psi, so then the resulting cochain will depend on p plus q elements plus 1, p plus q plus 1 element. I begin with A0. It will be equal to delta, so A0 phi p applied to A1 AP psi q A p plus 1 AP plus q plus the sum. So first I take the sum for I from 1 to p minus 1 to the power I phi p applied to A0 A I minus 1 AI AP. Right? But then we'll have, so in all these cases, whenever I is less than p, the product will, of AI minus 1 and I will stand inside the first bracket. Then we'll have the sum for I from p plus 1 to q p plus q minus 1 to the power, oh sorry, I forgot to say that there will be phi psi q applied to a p plus 1 a p plus q. So here we have phi p a0 ap, and the next will already be here. So we have a p plus 1 a I minus 1 ai a p plus q. And then in the end we'll have minus 1 to the power p plus q plus 1 phi p a0 ap psi q a p plus 1 a p plus q sorry a0 ap minus 1, sorry, and here I have, sorry, ap minus, again, sorry, I have to begin with p here, right? I have to begin with p here. Yeah? Okay. P plus q minus 1, ap plus q. Now everything is correct. Yeah? Okay, nice. So let me look at the first portion here. It looks pretty much like the sum you use to define the Hochschild differential. So the only thing which is missing is the term. So the first, so all these elements have the same factor psi q of AP plus 1 and so on, AP plus q on the right. So you can take this factor out. And what we have in the parentheses will look like delta phi, right, minus 1 to the power p plus 1. Sorry. Yeah. Phi. Oh, sorry. What to say that it is delta phi of A0, AP, plus minus 1 to the power p plus 1, phi A0, AP minus 1, AP, times psi q a p plus 1 a p plus q. So this accounts for the first two lines. Now the remaining part also has the same common factor, right? It's like this. So plus minus 1 to the power p. Because we start with not with minus 1, but with minus 1 to the power p plus 1. So we take minus 1 to the power p plus 1 in front of it. So what we have inside will look like, again, first we take phi of A0, AP minus 1. But then we have delta psi of AP plus Q minus, and the only term which is missing is this, is the first term here, minus A P psi Q of AP plus 1 AP plus Q. If you now expand this parenthesis, you'll see that this factor will cancel out with this factor. And what you get will be precisely equal to what you expect. That is the delta of phi p cup product with psi q is equal to delta phi p cup product with psi q plus minus 1 to the power p phi p cup product with delta of psi q. So it means that for all algebras, we have a product not only on cochains, but also on the cohomology. This product was discovered, I think, by Hochschild, and for a long time it remained mysterious, at least in case of non-commutative algebras. But in the beginning of 60s, Murray Gerstenhaber showed that for all algebras, the cup product in cohomology is commutative. To this end, he introduced a second important operation on a Hochschild complex, so-called Gerstenhaber bracket. So let again A be a be an arbitrary algebra. Let phi p be and psi q be two cochains of this algebra, Hochschild cochains of this algebra. Then we have the following operation. So first, we define for I from 1 to p the operation phi p circle sub I psi q to be equal to the following cochain, depending on p plus q minus 1 argument. And which is described by the following formula. You take phi p, then you take first I minus 1 argument and put it into phi p as they are. But at the ith place, you put psi depending on the next q arguments. And finally, you end with I1, AI plus Q, AI plus P plus Q, P plus Q minus 1, minus 1. So actually this I just shows the place at which psi appears in this string of the arguments. Now you define phi circle with psi to be equal to the sum. I'm afraid I don't remember the signs if you have the source. It's something like minus 1 to the power I times q minus 1, I believe. Phi p circle I psi q. Check the sign, please, if you have the source. So finally, here's the definition of Gerstenhaber bracket. You take phi p and psi q and define the bracket to be the combination phi p psi q minus 1 to the power p minus 1 times q minus 1 psi q circle with phi p. Is the sign, did I put the sign correctly? I think it's correct. Oh, yeah. Okay. Now it seems so. These constructions looks like just like some kind of arbitrary construction. The game you play with combinatorics. You do something. You use some plug in some signs. It looks totally arbitrary. It looks totally artificial, and it's a big surprise to know that this operation is in fact quite important and that it has lots of good properties. I'm not going to prove this theorem, however. The proof is just by combinatorics. You just go through the formulas and check that the identities hold. So here's the theorem. First, well, the properties of the Gerstenhaber bracket. First of all, it is skew-symmetric. Well, that's evident. Phi p psi q is equal to minus 1 minus minus 1 to the power p minus 1 times q minus 1 psi q phi p. That's clear. That's not very hard, actually. Now, the second statement is much more interesting. It says that the Gerstenhaber bracket verify the same type of graded Jacobi identity as this Houghton bracket. So this is proved by direct brute force computation, unfortunately, and I can have no advice except for, well, I recommend that you take a look in some papers by Gerstenhaber or in some other papers where this is done. I know of no, royal way to go through this computation. 3. Now, 3 follows from 2, so I'll go into prove this. Gerstenhaber bracket verifies the graded Leibniz rule with respect to the delta, to the boundary operator. Delta of phi p psi q is equal to, well, delta phi p psi q, and since I don't remember the sign, it will be plus or minus here. Delta phi p delta psi q. I'm going just to prove the last statement using the first statement and the following simple observation. Which is actually of some use in future. You can actually describe delta of some alpha is following in terms of the Gerstenhaber bracket itself. Actually, you consider the map M as from C2 of A comma A, which is given by just by the product of A and B. Right? This is bilinear map, so it's an element in Hochschild complex of degree 2. Well, why I don't want to go into details, because I actually need to introduce sign here to make everything work properly, but for the time being, we don't care about the sign. So actually, have the following identity. Again, up to the sign. It's almost evident, in fact, because what does it mean, delta? So what is M comma A alpha? It is a map of degree of alpha plus 1. So if alpha is if degree n, we have this, and it will be equal to M of alpha, so M circle 1 of alpha minus, it's minus 1 plus minus 1 to the degree, what was it? Of degree, I think it's n minus 1. M circle 2 of alpha, right? Then you subtract the sum of -1 to certain degrees. I don't remember to what. I think it's -1 to the power I. Alpha circle I M. Right? But what does it mean that you apply, say, the first term to this string of arguments? You get just M, where you put alpha at first in front, and then you multiply by the remaining element. Right? And the same here. You get, I think it's like this, A0, alpha, A1, AN. So up to the sign, these two are precisely the terms which appear in the Hochschild differential, an expression for Hochschild differential. And the same here. This part is responsible for the intermediate terms. So we have this formula now. Now the Leibniz rule follows from the gradient Jacobi identity and this expression, because delta of phi p psi q is equal to the Gerstenhauer bracket of M with the commutator of phi p and psi q. And then we can use the gradient Jacobi identity to express it in terms of these two summands. Nice. Before we proceed, I need to formulate the final form of the Hochschild-Rosenberg theorem. This form will take into account all the operations which I just described. So it sounds like this. Theorem. Sorry? It will be equal to something plus or minus M phi p psi q plus or minus phi p M psi q. So that's precisely what we need, because this is delta of phi, delta of psi, and modulo the signs. That's just what we want. Now the final form of the Hochschild-Rosenberg theorem. The map chi in the Hochschild-Rosenberg theorem from polyvector fields on M to the Hochschild cohomology of the algebra of smooth functions on M. Differentiable, of course, cohomology. Induces not just the isomorphism of spaces, but induces the isomorphisms of the algebras, induces the isomorphism of the algebras. That is, chi of the wedge product of P and Q will be equal on the level of cohomology, only on the level of cohomology. In cohomology. You should be warned by this, because if you try to compute the right-hand side in cochains, you will see that it is not true that chi of P and Q is equal to chi of P, chi product with chi of Q. That's not true in cochains, but that's true in cohomology. And also, chi of the bracket of P and Q, of the Schouten bracket of P and Q, will be equal to the Gerstenhaber bracket of chi of p and chi of q. Again, this is true only on the level of cohomology. Only in cohomology. The proof of these facts is actually surprisingly simple, modular the statement that it's actually much harder to prove this, in fact, than to prove to derive that formula. You see, both, if we know this formula, then we know that both maps on the left and on the right will verify the same. Oh yes, I quite forgot to say. Okay, since I'm in a hurry and I feel like I'm running out of time already, I'm starting to make some unnecessary statements, but still. So let me give again a few ideas concerning the proof. So first, you show that this is true. So to show this, we construct a chain homotopy between the left side and the right side. In cochains. So now this is a cochain. The existence of this chain homotopy is actually given by the Hochschild-Rosenberg theorem as we know it. Because if you symmetrize this part, you'll get precisely the same element, right? But when you symmetrize the right-hand side, you can show that symmetrization of the right-hand side will be equal to chi of p HQ. So it's a mere combinatoric to show that this symmetrization is equal to this. And now by the Hochschild-Rosenberg theorem, as we know it, the cochain between these two maps actually exists, just by the general result. As far as the second part is concerned, before we proceed with the second part, it is advisable to begin with a Leibniz rule which connects the cup product in cohomology and the wedge product. So first we prove that in cohomology the cup product and the bracket verify the Leibniz rule. And that's probably the most delicate part of the whole construction. Because here you again need to construct the chain homotopy intertwining the left side alpha, beta, gamma, and the right side beta, alpha, comma beta, cup product with gamma, and beta, cup product with alpha commutated with gamma. Now, the existence of this cochain intertwining these two is not so, well, it's not so evident. You really need to go into the construction of the Gerstenhaber bracket to obtain this cochain here. It is not something that you get on the nose. So it is equal to some cochain, to delta of something. H of alpha, beta, gamma. But once you know that this is true, you actually obtain this formula number 2 by mere exercise, because both left-hand side and right-hand side verify the same set of axioms. And we know that Schouten bracket is uniquely determined by this set of axioms. So the part 2 now follows immediately from this. And that concludes the proof. By the way, I mentioned that now you can actually use this type of brackets to show that the cup product in the level of cohomology is always commutative, even if your algebra is non-commutative. When you use Gerstenhaber bracket, you can consider the bracket induced by Gerstenhaber bracket on cochains on the level of cohomology. This bracket will, if you consider the operation induced by the cup product on the cochains on the level of cohomology, this cup product will always be commutative, even if the algebra was non-commutative from the beginning. Okay, so how much time do I have? Minus what?
-1.
Oh.
You have 4 minutes. The class ends at 5.
Okay, I have 5 minutes. Oh. You see, it is my purpose to consider so the purpose of having this theorem here, the purpose of having this operation is ultimate purpose is to use them when we consider the Kontsevich theorem. Kontsevich theorem actually shows that as far as the Gerstenhaber bracket is concerned, polyvector fields and polydifferential operators are the same. And now if you rephrase the associativity condition in terms of Gerstenhaber bracket, you will see that this sameness, this similarity allows you to go from elements in polyvector fields to elements in polydifferential operators. That's what they call the formality condition. However, if you ask me about just about the philosophical construction of quantization on the level on symplectic manifolds, in that situation I don't need all these structures. Philosophical construction is done in purely geometric manner, and it does not rely on any delicate homological construction at all. And therefore, when I was planning this course, I was expecting that between this part of the course and going to philosophical quantization, I'll have one lecture where I will describe the example of how this construction can be used to, for instance, in the same situation we already considered. I considered the deformation quantization of the dual space of a Lie algebra. And it can be done in this way again. It was my purpose to do this in terms of Hochschild cohomology abstractions. So I wonder if I'll have time next Thursday to talk about this.